is not an inversion theory. Yeah, I was saying some stuff earlier about this is a little more theory based, and because I want to explain the theory, I'll just do that, and we'll see how many problems. Thank you, Dulayu. We'll see how many problems I actually get through. I haven't put too many in there, but yeah. Let me share screen. Here. All right, you can see this window, correct?
Yeah.
All right. Moving points. Yeah. So there's a lot of things said about moving points, like how it's bad, and like how no one should use it. And this is not necessarily true, but moving points is tricky because if you do make a mistake, you're not really able to catch it. And you can make a mistake in a lot of ways. So the general strategy we're going to use for moving points, what I'm going to write here is not totally correct, and then I'll explain why it's not fully correct. But say we have a geo problem, and yeah, I don't know. Well, we're going to cover this one later. This is Pappas's theorem, right? Here. So just draw it, and then like, so we want to show this geo theorem. Let's see if I know how to do dotted lines. Okay, I clearly don't. I'll figure it out. But we want to end up showing some geo statement. And what we do is we move a point, hence the name moving points. So we're going to parametrize this point. Well, let's say we're going to move it, and we're going to move it such that it has coordinates p of t, q of t for polynomials p and q, and t is just like this is a parameterization, so t is any real number, and this is like any point that satisfies this. And we are going to then define the rest of the points and lines in this problem as some other, well, not exactly on the Cartesian plane, but because I have not, is this trivial that it moves on a polynomial? We're going to define it as it moves on a polynomial. And this will work when we animate a point on a fixed line, or like a conic or something. But it is not the Cartesian plane. That's what I'll get to after this. So we're going to then define every other point, like based on our moving point, as some other polynomial, ut, vt, and every line is like u of t x was like, oh yeah, sure, v of t y plus w of t equals 0. So we're going to have all these polynomials in terms of t that define each of the lines and points based on this initial thing. So let's say, right, like this point is p of t, q of t, and then this line, the equation of the line is dependent on t, and we say it's some other polynomial expressions and times x times y, right, and the constant term. And what we eventually get is that the problem is equivalent to showing that some large polynomial, what's a letter I haven't used, r of t equals 0. And to show that R of t is indeed 0, we have to show that for degree of R plus 1, values of t, R of t equals 0, and then like about like fundamental theorem of algebra or something, this is 0. And showing that degree of R plus 1 values of t, it equals 0, that's equivalent to showing that like for degree of R plus 1 points that like our animated points can be, we have that the problem is true. So instead of actually calculating all of these polynomials, what we're going to do instead is come up with a few shortcuts to instead calculate the degrees of the polynomials. So for any point p, for any point, we're going to calculate the maximum degree of the coordinates. For any line, we're going to do the same, maximum degree of ut, vt, wt. And then we will have a bound on the degree of the problem, right? The degree of R of t, and we just show for that many plus 1 values of t, our problem is true. Are there, yeah, Cartesian that without expanding is correct. But the first problem we encounter is that Cartesian coordinates are actually really bad because points at infinity are not defined. And points at infinity are actually like really useful when we're doing moving points. So what I'm going to explain now is the coordinate system that projective geometry happens in. Right, we define projective geometry as happening in the coordinate system. Here. Real projective plane squared, or real projective plane. And the reason why we use this is, as you'll see, points at infinity are well defined. And in fact, they're treated like any other point. It also makes our equations for lines and conics easier to work with. So what we're going to do is imagine in 3D space. Now, this is the point 0, 0, 0. This is the plane z equals 1. So what we are going to do is basically map all the points in 3D space except for like 0, 0, 0. I have no idea if any of this notation is standard, but I believe it is. So we are going to map all these points onto the plane z equals 1, and this will be like the real projective plane. So what we are going to do is we will take a point A, B, C. Let's say this point. I'm going to draw the line between 0, 0, 0 and A, B, C, and it will intersect. Actually, like this line can extend like this or that. It will intersect z equals 1. And in real projective plane coordinates, we say this is A colon B colon C. And the reason for the colons, actually, I won't do it here. We say that points with, imagine this is like a lambda. Right, so we say these 2 points, ABC and then ABC, all multiply by some constant lambda are the same. So if you have seen like Barry or something like that, it's a similar system to that. So importantly for our discussion on points at infinity, So we do our same projection sort of thing, right? We take a point ABC, we say like A colon B colon C, right, on the plane Z equals 1, right? So what happens if we take a point on the plane Z equals 0 and do the same projection? You can put in the chat, you can tell me. So like 1, 0, 0, right? We're going to say it intersects, right, our plane Z equals 1 at the point in projective or real projective plane 1, 0, 0. But like, because we have this
Can you just give like
visual,
an overview of what have you told till now? Because I joined 10 minutes late.
what did you say?
Can you just try to overview what you have told till now? I joined late.
Sure. So I explained the general strategy of moving points, which is that we are going to define a point that moves as in parametric coordinates with polynomials, and we are going to define all points and lines in terms of this parametric coordinates. And eventually we're going to see that the problem turns into showing that a polynomial with degree at most something is equal to 0. And we do that by verifying that for degree of that plus 1 values of t, it equals 0. I'll explain this general strategy later again. But basically, we are going to show that a problem being true is equivalent to a problem being true for some amount of cases of a moving point, hence the name moving points. And then we are going to just check those cases. And that is how you do a moving point solution. And what I'm explaining right now is that instead of in Cartesian coordinates, we do this in the real projective plane, which is like a different coordinate system where projective geometry happens, because the points at infinity are well defined. So what we do, we take 3D space, all the points in 3D space, minus the origin, and we sort of like smush all of that into a plane, and that's what the coordinate system looks like. So 0, 0, 0, and we're basically mapping all points to the plane Z equals 1 like this. If we have a point ABC, it maps to A colon B colon C, which are homogeneous coordinates, right? Basically, if you think 2A, 2B, 2C, and A, B, C, right, they will both map to the same point, and that is fine. That's how the coordinate system is defined. And the question I asked right now is, we say that 1, 0, 0, right, when we like compress sort of R cubed into a real projective plane, 1, 0, 0 goes to the point in RP squared 1 colon 0 colon 0. But the question right now that I pose is, what does this look like in our visual representation? Okay, so basically like what happens, yeah, I'll redraw this. Z equals 1, and we have our point 0, 0, 0.
It becomes the P infinity, right?
Did you say it becomes point at infinity?
Yes.
Yeah, it does. Right? So what we do is we define the point and we define here, 1, 0, 0 as a point in infinity of this real projective plane. So another way to define the real projective plane is to forego this visual representation. And okay, so a real projective plane, even though it's a plane, every point will have 3 coordinates. Actually, I'll do x, y, and z. And the real projective plane looks like the Cartesian plane, except we add points at infinity per this kind of mechanism. So I guess without the visual representation, we say that x, y, z is basically the same as x over z, y over z, right? If z is not equal to 0. If we go back here, right, when we draw the line between 0, 0, 0 and a, b, c, it on the plane z equals 1, right, this would be like a over c, b over c, 1. Right? So the important part comes when we let z equal to 0. So x, y, z will become, well,
Point of infinity.
what did you say? Audio is kind of bad.
Oh no, you can cut.
Okay. So we are going to say this is the point at infinity of the line between 0, 0 and xy, right? So we're basically adding points at infinity to the Cartesian coordinates almost. And we're making these homogeneous coordinates, right? So x, y, z represents the same point as like when we multiply all of them by lambdas. Right, so in this example, 1, 0, 0 in these projective coordinates is the point where we take the line between 0, 0, 0 and 1, 0, 0 and intersect it with z equals 1. So what happens is that we get like a point at infinity because, well, like this line and this plane intersect like infinitely far away. Okay. So the first advantage of this of using this coordinate system is that we have a definition for points at infinity, and in fact, a point at infinity is basically the same as any other point. Well, algebraically, it behaves the same, right? Like we have this homogeneous system, which means that we can write equations of lines that include the point at infinity that don't have anything like infinitesimally small, infinitesimally large. We can draw a line between 2 points at infinity. This turns out to be the line z equals 0, etc. I'll explain lines in the next slide. But basically, the last 3 slides, a recap is that we take like the set of points in 3D space, and we act as if we're looking at 3D space centered at 0, 0, 0, and like our eye lens is z equals 1. So basically everything in 3D gets smushed to 2D, and everything on the plane z equals 0 gets smushed to a point at infinity, or a line, and like all of them will form the line at infinity. Are there any doubts on this one? Or can I move on? You can PM me any doubts. Okay. I'll move on then. So we can look at what lines and conics, the equations of lines and conics, turn into in this new coordinate system where we like add points at infinity. So before, a line looked like ax plus by plus c equals 0, something like this. And now a line will look very similar, actually. Ax plus by plus cz equals 0. So in this equation of a line, we see that, if in our real projective coordinate system, right, if there's a point x, y, z that's on this line, then lambda x, lambda y, lambda z is also on this line, which is what we expect. And this is like very similar to the equation of a line in Cartesian, right? Like for all the Cartesian coordinate points, points which don't have a points which are not at infinity, we can say like so z is non-zero, right? We can say like z equals 1 because of the homogenization, right? We can multiply and correct lambda to make z equals 1, and then it looks exactly like this. And then for points at infinity, right, like the point at infinity of this is the point at infinity, right, of x plus by equals 0, where these lines are like parallel, right? And then that point in our new representation, right, this is exactly what we expect, right? Z equals 0 for a point at infinity, and then ax plus by equals 0. Here, I'll do conics on another slide. So in Cartesian coordinates, we would say that a conic is something of the form like ey plus f equals 0. And in the new coordinate system, real projective plane, we define this to be a conic. And this is like exactly the same, right? For points in the Cartesian plane, we have that like z is non-zero. We can multiply any point, or it is homogeneous, first of all, in coordinates, which means that everything has degree 2, right? So that that allows this to not pose any problems. And we have that for z non-zero, right? We can multiply some appropriate lambda so that this is 1, and then it looks exactly like our initial equation. So the second advantage of using this real projective plane coordinate system is that we're able to have like these kinds of we're able to have homogeneous equations for conics and lines, which will be slightly important later. Any other questions? So the main takeaway is that lines can be represented like this, conics can be represented like this, and these are exactly our same definitions of lines and conics as before, but now with points at infinity that we can put into these equations without having any problems. Okay, so now I can explain the actual general strategy for a moving points problem. So the first step, as I said, is to parametrize a point. So we are going to say that some point is going to be animated. It's going to move like this for polynomials p, q, and r, and t that is in the real numbers plus infinity. So we will also say that t at infinity, that t can be at infinity, and the way we allow that to be well defined is we're going to like divide. We can say this is the same. Well, imagine r is non-zero. We can do this kind of thing, right? So actually, yeah. So we're going to say r has like r has largest degree among these three. Then we can homogenize, or we can unhomogenize to make this one. This is q of t over r of t, and this is p of t over r of t. And the limit of this and the limit of this is not infinity. So this is a well-defined point in our coordinate system. So after we parametrize, we are going to find the degree of all points and lines in the problem. So the degree of a point is the maximum degree of p, q, or r, and the degree of a line is the maximum degree of u, v, or t. And we're also going to impose the condition that p, q, and r, or u, v, and w, are irreducible. So we are eventually going to bound from above the degree of every point and every line, if we can. And then we are going to say that the problem is equivalent to showing some polynomial is equal to 0 for every value of t, right? Which means the polynomial is 0. And we are going to say the degree of s is less than some like large number, right? Or maybe d. And then we are going to put in d plus 1 values of t into this equation and show that it is 0, which is the same thing as letting our moving point, the point that we initially parametrized, take d plus 1 positions and showing that for all of those positions, the problem is true. Okay, any questions on the general strategy or how we define the degree of a moving point or like a line? Or any questions about the real projective plane? Okay. So the first idea and the most important idea is what is called Zack's lemma, based on Zack, who helped create moving points many, many years ago. I think like maybe 4, I don't know. So, oh, this is like, well, okay, so first you're going to hear sometimes people, mostly Evan Chen, say like tethered and then untethered moving points. And Zack's lemma and everything we'll be discussing is part of untethered moving points, because tethered moving points is basically just untethered moving points where all the degrees of all the points and lines are like 1 or
What is
2.
that? What do you
What did
mean
you
by
say?
untethered? Untethered.
It's just a term that people use. So tethered means that all points in line, or all points will lie on some fixed line when we parametrize and we calculate the degree. So all points will lie on some like fixed line or some fixed conic. And then you can, and that's tethered moving points. So I'm just going to teach like what's called untethered moving points, where this is not necessarily true. And because like tethered moving points is basically just when like all the degrees are like 1 or 2. Well, for the most part. So untethered moving points, the biggest idea in this is called Zack's lemma. So if we have, actually I should probably explain before that. Okay, I'll just do it here. So if we have 2 moving points, so A and B, and these have degree A and these have degree B. So if there's 2 moving points with degree A, degree B, and we draw the line between them, then the degree of this line is going to be at most d of A plus d of B. And if A and B coincide for at k values of t, the degree is at most degree of A plus degree of B minus k. So, well, the idea that I'll be using is that if we have 2 lines, I'm just writing these as vectors. If we have 2 points, if we have 2 points, then the line between them which can be checked by like algebra, I think. So this is like a cross product. I'm just writing it out so that we don't have to actually deal with like vectors or anything. Wait, can I? So this is the equation of the line between any 2 points. This can be checked by like algebra, as I said. And then the most that, so let's say y1 is some polynomial, right? Z2 is some polynomial. The largest degree that y1, z2 can be is the maximum degree of all the polynomials here, plus the maximum degree of all the polynomials here. And similarly, the maximum degree of y2, z1 is the maximum here plus the maximum here. So the maximum degree of this coefficient of x is the sum of the maximum degrees here and here. And similarly for all the other coefficients, we get the maximum degree of all the coefficients in this line is at most the degree of this plus the degree of that. So where we get this k intersections or k coincidences, which means a and b for the same value of t are at the same point, right? We subtract k, comes from when I said that each of these polynomials, which I'm representing as x1, y1, z1, x2, y2, z2, the GCD of x1, y1, and z1 is 1, or they don't or some constant, but like homogenization can make that 1. So they don't share any linear factors. And so if these 2 points coincide, then we can look at the coordinates of this line. And for that value of t, let's say at t equals t0, x sub 1 equals x sub 2, y sub 1 equals y sub 2, z sub 1 equals z sub 2, or some constant multiplied times x sub 1, y sub 1, z sub 1, then, whoops, here we go. Then we get that this coordinate is 0, this coordinate is 0, and this coordinate is 0, which means there is a factor that is present, right? The factor t minus t0 is present in each of these polynomials. That is the coefficient of x, y, and z. So we can divide that out, and the maximum degree is 1 minus the amount of, or we can decrease the degree by 1 for every t0 that exists, which is where this minus k comes from. Any questions about Zack's lemma?
Can you explain how it works?
Can you explain the max degree part again of those matrices point?
Yeah, so we define the degree of a point as the maximum degree of the polynomials that the polynomials in T that make up its coordinates, and we define the degree of a line to be the maximum degree of a point that, or why did I say point? The maximum degree of a coefficient of one of the three coefficients. So, let's say there are 2 points, x1, y1, z1, x2, y2, z2. So the line between them is the line below. And the degree of this line is the maximum degree of each of the coordinates. So the maximum degree of y1, z2 is at most the maximum degree of x1, y1, z1 plus the maximum degree of x2, y2, z2, right? Because the degree of y1, z2 is the degree of y1 plus the degree of z2. So similar, I didn't hear exactly what you said.
But can't these polynomials cancel each other and make a zero polynomial?
Are you saying like y1, z2 minus y2, z1 creates something of a lower degree?
Yes, sir.
So we're just bounding the maximum degree.
Okay, so you are
Right, this
trying to tell the maximum can be this.
Yeah.
Okay. Yes. Okay.
So finding the actual degree is often a little difficult, but if we have a bound on the degree, then it works just as well, right? The final, we just need a number for degree of S, hopefully a small number though, or for this D here, we just need a hopefully small value for D. And then does everyone understand where this K part comes from? Why, if A and B coincide with some value at K values, then we can reduce this even further?
No, this was the part I was asking about.
Okay. Great. So we define so we can further define these polynomials to be irreducible, or like they're, well, not the polynomials themselves but irreducible, but the GCD of each of these is 1, which means that they don't share any factors, right? Or that there's no value of t that makes all of these 0. So if there is some value t equals t0 that makes A and B coincide, right? We have x1 over x2, y1 over y2, z1 over z2 are all the same, basically, right? Remember homogeneous coordinates. So like x2, y2, z2 is basically just some scaled up x1, y1, z1. Then we have that this equation becomes 0x plus 0y plus 0z equals 0, which means they all have a factor of all the three polynomials that make up the coefficients of x, y, z. They have t minus t0 as a factor, so we can just divide that factor out. And we can do the same thing for all values where A and B coincide. So if A and B coincide,
Right.
right. Okay, so we're good on the statement of Zack's lemma and the proof here behind it. Okay, so now I'll digress into things I should have said earlier. So first of all, in RP squared, 0, 0, 0 is not a thing. Basically, all other coordinates besides 0, 0, 0 exist. So just to clarify, right? And this does not pose any problems, right? The origin in Cartesian coordinates is 0, 0. In RP squared, we just say it has these coordinates. And okay, actually here, I probably shouldn't erase that. And the second thing I wanted to talk about before we get into the first problem is, well, it sort of alludes to a question that Bayo asked earlier, which is, can we ensure that when we animate a moving point on a line or a conic, that we get polynomial equations as the coordinates? And the answer is, for a line and conic, yes, we can. So if we have a line ax plus by plus cz equals 0, let's see if I got this. Then can define this as 1. Let's see if I actually can do math for a second. 0. We can define the coordinate of A as something like T. We can define this as like T minus C over B. Here we go. So these are all polynomials. These cover, and as T varies among like the points among reals plus infinity, this covers every point on this line. So that's how we parametrize lines. And for conics, what I'll do is I'll only show this for x squared plus y squared equals z squared. If you notice, this is in Cartesian coordinates, x squared plus y squared equals 1, which is the unit circle. And the reason I'll do that is, 1, I don't actually know the exact parametrization for the general form. And 2, if we take the unit circle or any conic in general, we can replace x with some linear combination. And we can replace y with some linear combination of x, y, z. We can replace z with some other linear combination of x, y, z. And doing this, we can create any conic. And the fact that our parametrization exists and is degree 2 will not change. So in fact, our parametrization, as I just said, will be degree 2. So the following, remember, we're looking at the maximum degree of each of these polynomials. Maximum degree here is 2, maximum degree here is 1, maximum degree is 2. So, and you can check this covers every point on the unit circle if we include t equals infinity. And yeah, as I said, has degree 2. So any questions on the fact that 0, 0, 0 does not exist? Oh, 5 questions. Oh, what is going on? Okay, I have no clue what's going on in chat. Maybe you PM'd me in Discord. I don't have Discord open. Unless you actually did PM me in Zoom, then tell me. So any questions on this one? Or our parametrization for a line or a conic?
That why did it take it like minus b by a times t and t minus c by b?
You talking about here?
Yes, yes.
Is there a, you're talking about if there's any problems with,
No, no, like why it took it like that? There should be purpose, right?
oh, why this like exact? Well, this works and it's the first thing I thought of. Like you don't have to parametrize in this exact way.
So you just try to give an example how to parameterize.
Yeah, yeah. I realized I had not actually parametrized this before.
Thanks.
I kind of panicked. Yeah.
Was it like, what if you set t as infinity? What does it do here? Like, which point does it represent?
T squared minus 1, 2t, t squared plus 1, you mean?
Yeah.
So these coordinates are homogeneous. So how we define coordinates when t is at infinity, as I said, is we just divide like this. So this is the same point as this one. And this one, we can see like a limit as t goes to infinity. 1, 0, 1.
Right.
Right. Okay, any more questions on this one? Okay. Okay, so we can go into our first problem, I believe. Which is, as I said before, also in the handout. Please look at that. If maybe I'm going a little too fast, because there should be like an overview of some things in the handout. Also, there's problems all listed in there. All right. No, one day I'm gonna actually figure out how to do dotted lines.
Maybe
in
just hold
Cubo.
mouse for some time and just keep it. Like draw partially lines. Small lines.
One day I will figure this out, but today is not that day. Here we go. So we want to show that these 3 points are collinear. I think I said like A1, B1, C1, A2, B2, C2. So I'll just do this one out because like I don't exactly expect you to be able to do this right away. Oops. So we are going to, we are going to animate C2, and it is going to have degree 1. As I said, here we can just animate it with degree 1. And let's use Zack's lemma to actually calculate the degree of all of these, all the lines and points. So A1 doesn't move. We can say it has degree 0, or we can say it has constant coordinates. Similarly with B1, C1, A2, and B2. So line A1, B2, it is also constant. We can say it has degree 0. Same with line A2, B1. And as a result, we can say that this first point of intersection has degree 0.
The rest two lines have degree C2, right? At max.
Yes.
Can you just repeat what you said?
Hmm?
Can you just repeat what you said?
So we're calculating the degree of all the points and all the lines, and it's going to become like one large polynomial eventually, right? So I say A1, B1, C1, A2, B2 all have degree 0. C2 has degree 1 by what I defined. And then this intersection, because line A1, B2, line A2, B1, they're constant. We're going to say 0. This has degree 0. It has constant coordinates. So similarly, line A2, C1 is constant, but line A1, C2. So this has degree 1, this has degree 0. So line A1, C2 by Zack's lemma has degree at most 1. And when we intersect it with line A2, I should have probably explained this one. But okay. So Zack's lemma, if we have two lines, A and B, then very similarly to Zack's lemma for points, Zack's lemma for lines, dA plus dB minus K. And proof is exactly the same as this. In fact, if you just interpret this here as the coordinates of a line, x1 times x plus y1 times y plus z1 times z equals 0, do the same here, and switch out x, y, z at the bottom as just the coordinates of a point, is exactly the same formula. Yeah. So now that I remember to do that, I'm on a roll today. A1C2 has degree 1, A2C1 has degree 0. So this intersection has degree 1. Similarly, this other intersection has degree 1. And to calculate the full,
I guess it can at max have one, but if
well, yes, can at max have 1. So
Okay.
in future, yeah, you are right. When I say has degree blank, just interpret that as has max degree blank whenever
Okay.
I'm solving a problem.
yes,
Okay. So so to finish, well, I'm gonna write this in terms of matrices, but like matrices are not necessarily needed. If we have 3 points in RP squared, similarly to if we replace this by 1, right, the same formula holds in Cartesian. These 3 points are collinear if and only if this has degree 0. No, this is equal to 0. And what that means for moving points is that when we expand this out, imagine A1, A2, A3, so on are all polynomials. And right, these are the maximum degree of polynomial. The first row, let's say it's D1, D2, D3. Then the degree when we expand is D1 plus D2 plus D3 at most. Right, we're basically doing some linear combination of a term in the top times a term in the second row times a term in the third row. So to show that these are collinear, that turns out to be a polynomial of degree at most 1 plus 1 plus 0 equals 2. So we need 3 values. Remember, we have to do this and then add 1. 3 values. It's actually pretty common to just say we need 2 values and then your entire solution becomes null. 3 values of C2 for which Pappas's theorem holds for the problem to be true. And in this example, we can choose 3 values pretty easily. C2 equals A2, C2 equals B2, C2 equals this point here. I don't want to give it a name. So since, huh?
Just give it name D1.
I cannot really hear that well. Okay.
He meant to give that a name, D1 or something.
D1. D1. All right. Thank you. So for these 3 values of C2, the problem is true. So the problem is true in general. And that's how we prove Pappas's theorem. So this should feel like, well, at least for this example, it should feel like a little of a hack, just because
It's
3
like a bit of cheating.
well, yeah, I guess it is, because there's 3 easy values that all make the problem basically degenerate, or like be very easy. And then all of a sudden we're done. But it is not always so easy. And we've only defined this for points and lines. So if there's any conics, then we don't really have anything to do. And like if there's any rotations, we have like nothing we can do. But this example, well, after this example, I want to like say a few things that I should have probably said earlier. Right. So first thing, this works exactly the same when we want to show 3 lines concur. We just sum up the degrees, the degree bounds that we have. And the second thing is that Zack's lemma is actually very tricky. So Zack's lemma, right, caveat. So when so let's say for some value t0, right, we show that points A and B are the same, right? A equals B. Then we can factor out t minus t0 from the equation of the line between A and B. So once we do this, we really don't have any idea what this equation looks like when we let t equals t0. So in some cases, we do have an idea of what this equation looks like, but in most cases, we don't. So a common mistake is to decrease the degree of line AB by saying like, oh, at t equals t0, we have that A and B are the same point. And then when we're checking our 3 values or however many values we need to check, we say, oh, at t equals t0, the problem is true. But in fact, we don't know if the problem is true because we're working now with the polynomial version of a problem where we have like taken out the possibility of t minus t0, right? So unless you know what the line looks like when we factor out t minus t0, you can't use t equals t0 as like a point when checking if the problem is true for so many cases. Here, I'll just put some exclamation marks because this is important. Because like apparently people mess this up a lot. Okay, let me actually read now for the first time the list of things I was supposed to actually cover.
So like, let's say we have some like nice configuration only when A equals B. Like we really want to take that as a case. So like in that case, Zack's lemma is kind of useless, right? Because you need other points anyway.
Well, we have, okay, we have the degree of A plus degree of B bound anyway, but subtracting the K is useless, right? If we have T equals T squared. But remember, if we just have like any 2 points in being the same, it doesn't necessarily mean that we have used the case where T equals T0. If you define the setup in such a way where you never have to interact with T0, because you never have to use the line between A and B, then it's fine.
Right.
Right, okay. So we can still have nice configurations. It's just unfortunately, with moving points, you can't always be like really dumb. Yeah. So what I tend to do is just not use this minus K, or where did it go? Oh, it was probably back here. Okay, I tend not to use this minus K a whole lot because like I'm always worried I might not have like counted right, but I'm presenting it here because people do use it and it is apparently really important. All right, okay, we have 15 minutes left. I think I can explain this next theorem, next couple of theorems. Okay, so this next theorem, it basically allows us to deal with rotations, which, as we'll see in our second example, ends up being like kind of important. So like, whenever we want to define like, whenever we want to deal with circles, we can instead think of, we can sometimes think of it as like rotations. We want to show like we rotate, or like here, silly example, right? We move this point along the line. We have this point is fixed.
So it's
Draw a circle. We want to define what this point is, or we want to find out its degree. What we do is we just, here, I'll give these names. These will be the brethren of D1. D5. Right, we can just say that we define D5 as we rotate line D3, D4, right, around D4 with 180 minus this angle. And then we let it intersect this line here. So it allows us to deal with cyclic quadrilaterals. Okay. So the lemma that I'll show, we generally don't use this in its full power. Like the example I just showed, we don't use in its full power. I might, or I probably will use its full power in the next problem. So we have points at infinity, A, B, C. Let's say with like degree dA, dB dc, then the point at infinity, so let's say like this is like the origin or something I'm drawing. There's A along this line, B along that line, C infinitely far away here. And I want to find the degree of D where we have this angle equals this angle. And I'm going to say degree of D is less than or equal to. So often we're going to deal with something where A and B might be fixed, as in the previous example. We want to rotate a line by a fixed angle. We can interpret that as rotating it, as we can say A and B are fixed with that angle we want, right? So degree of A is 0, degree B is 0. And we get something like degree of C only. So
how is that C defined to be? Is C defined to be an arbitrary point?
C is defined to be a point at infinity as well.
Okay.
And we want to find the degree of the point D at infinity that's like this.
Okay, so point of infinity of line, what?
The line that I just drew here.
Okay.
C is the point of infinity. So basically we want to find D where this angle equals that angle. And basically this is like we can say like the coordinates of D, like D1, D2, 0. Similarly, we can do the same for A, B, C. And then we can look in terms of tangents. Actually, we can be even maybe like a little more slick if we want. We can say a 1, D1, 0, so on. And we're basically saying that the tangent of the angle between the line like y equals 0 and the line between 0, 0 and this point at infinity D, the tangent of that angle, delta, whatever, is D1. And we also have that the tangent of that angle, we have like delta equals, I'm going to say the angle for A is alpha, the angle for B is beta, the angle for C is gamma. We have that delta equals alpha plus gamma minus beta, right? We can see here, we want like, actually, maybe I should have done this. Maybe I should have done this a little different. Yes, here. Sure, it's the same problem, basically, right? So this angle between beta and alpha, we want to add that to gamma, and it's going to make delta. And then we can do like tangent things. Right. Tangent of delta is tangent of alpha minus beta plus gamma. We can write this in terms of tangent of alpha, tangent of beta, tangent of gamma. And that'll be very fun. Hopefully you get the idea at this stage of me writing this out. And then we can define, right? We have tangent of alpha minus beta. Again, it's like something like this, right? We sub that in here. We get some like ugly thing. But then we get that if the coordinates of A are like A1, A2, 0, right? B1, B2, 0, C1, C2, 0, then we get that it's a linear we eventually get that we have a linear combination of one of the things here, a linear combination of products where it's one of the things from A, one of the things from B, one of the things from C that has degree at most degree of A plus degree of B plus degree of C. So that ends that proof, right? We get this sort of thing. So the next problem, I think I didn't put this in the handout, but I'll see how it goes. So we are going to have 4 lines. So L1, L2, L3, L4. So we want to find a bound on the degree of the statement that these 4 intersections, let's say this is L1, L2, L3, L4 at the top. We want to find a bound on the statement that the degree of these, of the sum of these, or wait, why did I say the sum? We want to find a bound on the degree that of the statement that these 4 points are cyclic. So what we will do, so we have that by Zack's lemma, right? We have that the line at infinity is a line with degree 0, it's constant. So the degree of L1 is like an upper bound on degree of the point with L1 and line at infinity. I'll just say Z equals 0. So we basically end up with 4 points at infinity. They all have degrees at most degree L1, degree L2, degree L3, and we can just say L4. Yeah, sure. So yeah, L1, L2, L3, L4. And we want to show that, so we have L1, we have L2, we have L3, L3, L4. The points at infinity of each of these lines. It's an artistic representation of it. And we want to show that basically the angle between these is the angle between these, right? Remember, that's a definition of cyclic. These angles are the same. So we want to show that this point with degree of L4 or less and a point with degree L1 plus degree L2 plus degree L3 are the same. So this statement, or if we want to show that 2 points are the same, we have like, let's just say x1, y1, z1, x2, y2, z2. So what we can do is we can homogenize it. So x1, y1, z1, y2 times the sum, z2 times the sum, and we define, and we homogenize x1, y1, z1 similarly. And now both of these have the same, both of these coordinates have the same sum. And we want to show that it's like exactly the same. So we can just like subtract like that. And we want to show that these are the exact same. And basically the maximum degree here will be degree of this plus degree of that. So the maximum degree of the coordinates in each of these polynomials is the sum of these two degrees. So basically, we have three polynomials with degree this plus degree that, degree of this thing plus degree of that thing that we want to show are all 0, which is a statement that has degree at most this thing plus this thing. I should probably give things names. But the moral of the story is that if we want to show that a point with this degree and a point with this degree are the same, we need, this statement is a polynomial with degree at most. There. So we have a bound, which is good. Atul, how much time do I have left? I actually don't know when these classes end.
Oh, around like 15.
Oh, okay, 15 minutes more time. Okay, what can I do with 15 minutes more time?
Like you can end the class now if you.
Can we
I'll
try like one problem?
Yeah, sure. What's it? Actually, no, there is one more thing I will talk about. Sorry, quick guys. But this will not take a long time. So if we have 2 points, A and B, this has degree A, this has degree B, then what is a bound on the degree of the point, which is like, well, I'm just gonna say like K A plus like 1 minus K times B, which is basically like a point on line AB that is like K here. So like this would be K, this would be 1 minus K. So basically if we have 2 points A, B, then some like fixed like linear combination of them, right, will be what we want to bound the degree of this. Yeah. So, okay, yeah. What we do is the same homogenization thing I said earlier. So we write them so that they have the same, so that each of the coordinates of A and the coordinates of B have the same sum. And we basically, and that basically means that each of these new representations of A and B have degree A, have at most degree of A plus degree of B degree. And then we're able to combine them just like this, right? K times like A prime, which is the new representation of A, plus 1 minus K times B prime, which is the new representation of B. Actually, I'll write this out. So A1 prime, A2 prime, A3 prime are the new representations. B1 prime, B2 prime, B3 prime. And then to get K times A plus 1 minus K times B, which is like this linear combination thing, we can literally just do KA plus 1 minus K B1 prime dot dot dot. And this has degree at most A plus B, or degree of A plus degree of B. So let's see what to think. Okay, do I remember the statement of this problem? Yes. So we will do like one, maybe two more problems. This one isn't in the handout, but like it's not bad. Okay, so we have a triangle A, B, C, and we have a variable point P. As I showed with the Pappas theorem statement, they might not always give you a variable point P in the problem, but if they do, and varying that point P is worthwhile, then that's a good, that's good for you because now you know moving points. So we let E and F be such that PC equals PE, PB equals PF, and want to show that circle AEF passes through a fixed point. So okay, since I guess you, or at least Kurtar, said that y'all wanted to do a problem, does anyone have any ideas on how we would start this? Because at the moment, writing PC equals PE is a bad definition of E if we are to do moving points.
Wait, so what is the problem? Sorry, I could not listen.
PC equals PE, PB equals PF, show that circle AEF passes through a fixed point. So first, how can we define E and F in such a way that's maybe more helpful with moving points? So remember, we can do rotations now. So I mean, like that might not be like directly applicable to showing PC equals PE, but like, yeah, we can do rotations and we can do linear combinations. Okay, okay, I will do this one here. So what we can do is we can let this be like PAC. We can let the foot from P to line AC intersect AC at a point, and we can let E be the reflection of C across PAC. So why this is more calculatable in terms of moving points, okay, so we can start writing the degrees of all the points. So this is degree 1. And to define the line between P perpendicular to AC, we can just say this is the line between P and the point at infinity, which is perpendicular to AC. And that point at infinity is fixed. So it has degree 0, and then P of AC has, this line has degree 1 by Zack's lemma. Line AC has degree 0, it's constant. So the intersection of those two lines has degree at most 1 by Zack's lemma. And by our new linear combinations thing, we have C is degree 0. So we can say E is like 2 times like minus C, right? We reflect C over a piece of AC. So E has degree at most 1 plus 0, right? E has degree 1. Similarly, we say F has degree 1. So now, how can we, okay, so let's say our fixed point is Q, right? Let's say we already know, but just for purposes of showing the power of moving points, I'm gonna say we don't know what Q is, but let's say we did know, just imagine. Then what would the degree of the statement be? Because I want to show that there is some fixed point Q such that angle FQE is fixed. Okay, so what we can do is we can look at our rotation theorem. So we basically want to show that if we have a line FQ, we rotate it 180 minus angle BAC degrees clockwise. It intersects at another point E prime on AC. We want to show E is equivalent to E prime. So
Can we just show that it intersects at degree 1?
what did you say?
Can you just show that E dash is degree 1, which is suffice?
Which is degree 1, E prime?
Yes, it does.
Well, if we have that E prime, E dash is degree 1, right? There are a lot of degree 1 points on
Yes.
like line AC. Or there are a lot of degree 1 things on line AC. So we don't necessarily have that E is equivalent to E prime, right? Like not every degree 1 parametrization is the same on a given line or conic.
But if
But
you like some point have E equals to E prime, and if we show that both are linear, so does that not show anything?
degree 1
mean-
is not necessarily linear, because if we have a
Right.
representation like AT plus B, CT plus D, ET plus F, then we have that this is degree 1, this lies on a line, but they're not linear.
Right, so
Or
still
it's
if
not
we
a
showed
linear
it for
movement.
like if we showed it's the same for two like cases,
2 cases would not be enough. right?
Why
Like,
exactly?
okay, I'll rewrite this like this. Whoops. So this is another, this is also degree 1, but this is not like linear movement as we would typically expect, right? Like something like 1 over, like, so we can say t, so, okay. If we look at Cartesian coordinates, right? T0, 1 over T0, right? Like we would say T comma 0 moves linearly, 1 over T comma 0 does not move linearly. However, they both have degree 1 when we define it like this.
So,
But we can, in fact, do this homogenization sort of thing to get that if they intersect for 3 points, it's fine. We show that they're the same.
right.
So in fact, this is what we'll do. And the reason why E dash is, or does have degree 1. Okay, so this is slightly involved. So line FQ, F has degree 1, Q has degree 0. By Zack's lemma, the degree is less than or equal to 1. So the point at infinity of line FQ by Zack's lemma has degree 1. So now we can rotate this F by a fixed angle. So the degree of that point at infinity is degree 0 plus degree 0 plus the degree of the point at infinity of FQ. This is 1. And then we have that E dash is the intersection of line AC, which has degree 0, and then the line between Q and this point at infinity, E dash Q point at infinity, which has degree 1. So by Zack's lemma, this has degree 1. So basically things that, so Zack's lemma is very useful, first of all. And so think of so points and lines are sort of interchangeable in the sense that basically like the line at the line FQ has the same degree as the point at infinity of line FQ by Zack's lemma, right? We're intersecting it with like we're intersecting line FQ with a constant line. So by Zack's lemma, they have the same degree. So we have E dash is equal to 1. E has degree 1. E has degree 1. So the entire statement has degree 2, which means we need to show that for 3 values of P, or for 3 values of E, whichever moving point you want, for 3 values of P, the statement is true. And the important thing is that we didn't use any special facts about Q. We just know that if the problem is true, there's a fixed point, and the problem has degree 2, and we need to show for 3 cases. So for 3 cases of P, we're good. And yeah, as I said, we didn't use any special facts about Q. We don't know anything about Q as of yet. So when we're actually writing this up, we're gonna want to replace Q with the actual point, which we will find soon. A, B, C. Okay, I'll just do this. P is equivalent to C. So when we're looking at the problem for special cases, we want to be a little careful that we're defining this, right? When we say P is equivalent to C, right? That we're doing the problem based on our definition of degree or how we set up the problem for moving points. So instead of saying, oh, if P equals C, then everything is degenerate at the end, right? We want to be a little more careful. So the line between P and this point at infinity intersects line AC at C. And then the reflection of C over C is C. So instead of like everything degenerates and like the end, right? We can just say that E equals C in this case. B, this one's well defined. It's this point where like these angles are the same. And this circle, what does it pass through? Any guesses?
Humpty or something.
What did you say? I heard like the last. I didn't hear anything of what you said. I'm sorry.
He said Humpty or something.
Said my audio, I guess, is really bad today.
I am saying he said, is it Humpty or something?
Oh, it is not Humpty.
The Orthocenter,
Yes, it is the Orthocenter.
because
Right.
the angle
So-
is right and you can take the midpoint also.
Oh, that's the cosine.
Sure. Right. So angle. So if you say this is like H, right? Angle AHC equals angle AFC, 180 minus angle ABC. Everything is good. Similarly, if we let P equal B, get the same thing. So we just need one more value of P. And I think Atul said like midpoint. I think he did.
Yes, he
Not
said.
Yeah, because then E and F become feet of altitudes.
P equals B plus C over 2. All right. Yes. We get foot of altitudes, we get this. All right. So that's the problem. That's it. So we're able to calculate the degrees of everything in this problem using the previous couple facts, Zack's lemma, and then rotations, and then homotopy for like linear combinations. And without knowing what this point Q was initially, without knowing that it was the orthocenter, we're still able to calculate the degree of the problem. And then, yeah, we just like do special cases. Hopefully the special cases are easy. Sometimes they're not obvious, but they're still easier than the original problem. And then we're done. So I think I went a little over time right now. Pranav told me that if I needed another class, I could do it Tuesday. So I will confirm this with Pranav.
Yeah, I can just confirm right now if you want, by the way.
Okay. Is this true?
Yeah, like I can just check on the schedule.
Okay.
On
So-
Tuesday, wait, not Tuesday. Wait, I told next Tuesday. When?
Yeah, you told next Tuesday.
I don't think that's possible anymore because like today's class was cancelled on inversion theory, right? So,
Yeah, I see.
but
well,
I think 18th of August would work. That's
I
after
cannot-
17th.
cannot
18th or
do
19th.
18th. I cannot do those days, but something will be worked out probably. most likely next weekend or like a weekend after. And I will continue moving points lecture.
Yeah,
But
sure.
that's all I have today. Yeah.
So I stop the recording.
Sure.
All right.